All right, so the recording should be on right now. I'm just out looking for the confirmation on my side. Yep, okay, it is on. All right, so we are moving on to binary addition today. So we are trying to add numbers in base 2. So there are several ways to look at this, but the way I'm going to look at this in this class is we already know how to do that because of what we learned on Monday about addition in base 10. So we'll go ahead and continue with that trajectory. So let me go back to the notes here so that you know where we are at with base 10 addition. Oh, this is the other thing that I can do today, which I think may be helpful because this way you guys would not need to write down everything on the whiteboard either, because I think I can get my tablet to work with my stylus. So whatever I draw, on my laptop computer, it's going to be projected, also on the other side. It's just that sometimes I need to lay my screen down flat like that. All right. So what we talked about on Monday is a structure of how we perform multi-digit addition. And the key concept is, how do we name all those digits, floating around? Okay. So I'll give you an example again, so that we have a context of, talking about, all of those concepts. So let's just say that we have 600. Oh, this doesn't work. It's still offset, because I don't know why it is still offset. Let me see. I tried this. I know why. Okay, I think I know how to fix this problem. Let me give this a try and see whether the problem is fixed. Give me a second here. Because the resolution of the projector is not the same as the resolution of my built-in screen. So I think there might be a scaling issue because of that. So what I'm doing is I'm changing. Oh, this will mess up OBS, I think. Okay, that is not good. Okay. All right, so I can't do that either. And it's still streaming. Let me see if the stream is broken. Sorry about this. The streaming is good again. All right, so that's good at least. All right, so I still cannot use my tablet, to capture, stuff that I write down on the whiteboard. So I still have to write stuff on the whiteboard. I will try to do it in a way where I don't need to erase anything. So at the end of the class, you can just kind of walk up here, take a picture, and that would be, a record of what is on the whiteboard. You can also, just write it in your notebook as well. All right, so let's try 647 plus 156. There we go. So we already have explored this, how to get this done. 7 plus 6, the single digit sum is 3. 4 plus 5, the single digit sum is 9. And 6 plus 1 has a single digit sum of 7. So that's what the R function does. And then now we have to compute the carry bits. The carry bit over here for digit 0 is assumed to be 0, okay? But it doesn't have to be 0, but right now we'll just say that it is assumed to be 0. And then 7 plus 6 has a carry of 1, it goes here. 3 plus 0 does not have a carry, so we don't have to add one more to this one over here. And now we have 9 plus 1, which is 0 with a carry of 1. So we have a 0 here with a carry of 1. And then 3 plus 0 is a 3. 7 plus 1 is an 8. And that's how we got to the answer of the multi-digit addition. So this is just a quick run through of how we did the math. But one thing that we also did on Monday was we started to name the individual digits, okay? Because with the names, I can now refer to each individual digit and express how it relates to the other digits. So all of this stuff here is still just a review of what we talked about on Monday. So these are the columns: column 0, column 1, and column 2. Column 0 is corresponding to bit 0, or I shouldn't say bit 0, but digit 0. Column 1 is corresponding to digit 1, and column 2 is corresponding to digit 2. The rows are named. This is X, this is Y, this is Q, this is K, and this is S. So that's how things are labeled at this point. Q of I, which is I is referring to the column, is expressed to be R of Xi, Yi, and then we try to calculate the sum. So S of I is also just R of, but this time it would be Qi, Ki. This one is new. I haven't really talked about this on Monday, but it kind of makes sense because the single digit sum between the Q and the K is the sum. So the one that is tricky is the carry. So K of I plus 1, which means it is one column to the left, is we calculated that to be C of Xi, Yi. And somehow we also have to factor in Q of Qi, Ki. So I believe this is all discussed on Monday. And then on Monday, we also said, we can use a plus here. The question is, do we need to use a plus? Because we don't know how to implement addition using logic gates. That's actually what we're trying to figure out with this module. So we said, so I said, it would be nice if we don't have to use addition. If we can substitute this addition to be a logical OR, that would be best, okay? But you may or may not be able to use an OR in place of the plus, depending on whether this carry term, the C of Xi, Yi, and the C of Qi, Ki can be true at the same time. So that was kind of where I left off. I left behind some argument, but that was incomplete as a proof, and it was done, I think, after the lecture. So what we'll do today is to look at these two carry functions and try to reason out, can they both be ones? Now, technically speaking, I should use proof by induction on top of the logic that I'm going to present, but I'm not going to do that, okay? Because it's just a little bit out of scope, and unless you have taken CISP310 already, you may not understand what is proof by induction. So that part is not going to be very helpful. So what we want to do now is, I'm going to try to use the whiteboard. I mean, not the whiteboard, but the projector, to capture this part. So I want to capture as much as I can using the projector, just so that you don't have to copy or you don't have to later on take a picture. So I'm going to use Joplin. This is Joplin. On the left-hand side is what I actually type, but what you want to do is to focus on the right-hand side, which is the rendering of what I'm typing. So now I want to figure out C of okay, so $, can be used to enclose a math equation. So now I want to look at the actual equation of K subscript of I plus 1 being defined currently as C of Xi, Yi, oops. And then we use a plus for now, and then we have C of Qi, Ki. All right? So let me just ask, do you guys have any questions about the use of the plus? Basically it says if this carry here can be coming from x0 plus y0, it can also be coming from q0 plus k0. So is that part okay? All right. So now the question is, what does it mean if C of xi, yi equals to 1? So we want to do some reasoning here. So C of xi, yi being a 1. And I'm going to close the equation first just so that it renders. What does that imply? How can it happen? Or what can be implied out of that? Yes, go ahead.
I would guess either xi is 1 or y of I is 1, but not both.
Okay, well, we have a carry situation, right? So that means the sum of xi, yi has to be greater than or equal to 10, because
Right.
that's how we define the carry function. So going back to the notes, okay, let me go back to the notes first. The carry functions were defined here. You can see how the carry function is just returning whether the sum of x and y is greater than or equal to 10. So now when we go back to the notes here, we can now say, okay, so if it is a 1, that means, xi plus yi is greater than or equal to 10, or whatever base we choose to use, but in this case, it's base 10. Okay, so that's kind of interesting, but I'm going to say one thing here, and you guys can say whether that makes sense or not, okay? So I'm going to claim that this implies um, r of xi, yi has to be less than or equal to 8. Does that make sense to you? Okay, so we'll just look at this implication here. So we'll focus on the right-hand side because that's the actual math notation that I want you guys to pay attention to. So does that make sense? If xi plus yi ends up with a carry, we can guarantee that the single digit sum between xi and yi is less than or equal to 8. And if so, why is that the case? Go ahead.
Well, if there's a carry is 1 and if it's 9, wouldn't that make it go, like, move it over more?
You're almost there. Go ahead.
There's maximum 8 because the highest numbers you can add is 9 and 9, meaning you
Exactly.
still wouldn't be able to get 19%, because that would require a double digit at that point.
Yep. So that's the complete answer, but you're on the right track. So good job. So that's because xi is a single digit in base 10, which means it can only range from 0 to 9. Same thing for yi, it is a single digit, it can only range from 0 to 9. So the most you can get is 9 plus 9, which is only 18, but that means the single digit sum is just 8. Now, if the carry of xi plus yi is not a 1, you can end up with a 9, because 0 plus 9 is a 9, 1 plus 8 is a 9, 2 plus 7 is a 9. But if you have a carry, that means the summation between xi and yi has to be greater than or equal to 10, and as a result of that, the remaining portion of the sum has to be less than or equal to 8. Does that make sense? It has to do with mod, by the way. So is it intuitively okay? All right. All right. So in return, what does that, how is this, going to help me? Well, what I did not tell you, what I neglected intentionally to tell you, that this is also Q of I. That's how Q of I is defined. All right? You go like, okay, big deal. So what if Q of I has to be less than or equal to 8? Well, that's, because now we can, carry out the implication one step further, because now we can say the C of Q of I, K of I, is guaranteed to be a 0, which is what I really want to demonstrate. And you go like, why is that the case? If Q of I is guaranteed to be less than or equal to 8, why can I then guarantee that C of Qi, Ki has to be a 0? What is the rationale behind that? I mean, and this is the part where proof by induction really should have been used, but I'm not using it. What do you think is the range of value of K of I?
From 0 to 1.
0 to 1,
Yeah.
exactly. But that's in a way is a circular reasoning, because the whole thing is to prove that K of I can only be 0 or 1, but I'm yet relying on the fact that it has to be ranging from 0 to 1 to make this entire thing true. So this is why I really should have used proof by induction, because proof by induction says if K of 0 is guaranteed to be between 0 and 1, then I can work on the other ones and make sure that they're also between 0 and 1. But we can kind of let it go and assume that K of 0 or K of I is also ranging only between 0 and 1. If that is the case, if Q of I can only go up to 8 and K of I can only go up to 1, in the worst case or in the best case, depending on how you look at it, 8 plus 1 is 9. It does not end up with a carry. Are we good? Are we doing okay so far with this part? All right. So if this part is okay, then we go to the opposite, which is basically looking at the carry bit of qi plus ki. And we ask, what if this is 1? What is that going to imply? That is what I'm asking. Well, if qi ki is a 1, and we know that ki can only range from 0 to 1, and qi can only range from 0 to 9, what is that telling you? Can we lock down the exact values of qi ki? First of all, okay, so look at the example here. This is the situation where qi is a 9, ki is a 1, and that ended up with a carry to the next column. All right? So now the question is, are there other cases than this that can end up with a carry because of the addition of qi and ki? The answer is no. There are no other ways. Why? Because qi is a single digit. In base 10, it can only range from 0 to 9. Ki, on the other hand, because of what we saw earlier, can only range from 0 to 1. So that means the only way we can end up with a sum that is greater than or equal to 10 is qi has to be 9 and ki has to be a 1. So that is tremendously helpful because now we lock down the value of qi being 9 and we lock down ki being 1. All right. So what does that imply in return? Why is it not turning into math notation? Oh, because the dollar sign not being there. There we go. So what is that in return going to imply? So this time, k of I being 1 is not very important. Go ahead.
So in that case, C, xi, and yi would equal to 0.
It has to be 0, but
Yeah.
why is that the case?
Because it doesn't have a carry because we have qi being 9 and ki being 1.
Yep.
Yeah.
It has to do with qi is a 9.
Yeah, qi is a 9.
Mm-hmm. So now we say, C, oh, there we go, wrong place, okay. So this in return implies xi plus yi, y underscore I, the whole thing mod 10 is 9. How do we know that? Because that's how R is defined. R is x plus y mod 10. So and also Q of I is R of xi yi. So that's why I now know that the mod of the sum of xi yi, okay, xi plus yi, the whole thing mod 10, has to be 9. Okay, but how is that going to help me? Well, there's one extra constraint. Xi is a single digit in base 10. Yi is also a single digit in base 10. So somehow I'm adding a quantity from 0 to 9 to another quantity from 0 to 9, end up with a sum, and if I mod that sum with 10, I end up with a 9. So what is that telling you? Now, just because you know the result of a mod doesn't mean that you can lock down a specific value. Because if I know the remainder of a division after the division by 10 is 9, in this case, that means the sum can be 9. It can also be 19. It can also be 29, 39, 49, and so on. Because it's only the remainder after division by 10 that I know that I can confirm being a 9. But because we also know that xi can only range from 0 to 9, and we also know that yi can range from 0 to 9, that helps me to lock down and say, oh, so that means xi plus yi cannot exceed 10, it cannot even reach 10. So this implies, right, so I need a right arrow, C of X, I, Y, I has to be a 0. So I'm not sure whether you guys are following the math or not, um, but trust me, there's no magical, super, complicated math here. It really has to do with just arithmetics. We're just dealing with addition and comparison. Well, and also mod, which is division. Okay, so now the question is, so what? I mean, what is the big deal? Okay, so what is the big deal? If you look at these two long chains of, well, not really long, but chains of implications, and let me just kind of give you a summary. Okay, so I'll summarize and get rid of the stuff that is not really important because I just want you to focus on the end results here. So that's one end result. And let me work on the other one too to give you just the summary without the mechanical part, of what goes in between. So I just have to get rid of all of this stuff here. All right, so when you look at these two simplified statements of implications, what is that telling you? If C of xi, yi is a 1, it guarantees that C of qi, ki has to be a 0. If C of qi, ki is a 1, it guarantees that C of xi, yi has to be a 0. What is that telling you? What is the result? In other words, if I were to ask you, can both C of xi, yi and C of qi, ki, can they both be ones? What would be the answer? It has to be a no. Okay. Wow. So how is that going to help us? It means we don't need addition anymore. We can just use the or. You go like, how does that work, right? So I'm going to give you a truth table. So we got x, we got y, and then we have x plus y, and then x or y. So this is not exactly a truth table because we do have a sum over here. 0, 0, 0, 1, 1, 0, 1, 1. X plus y, not surprisingly, is 1, 0, 1, 1, 2. X or y is 0, 1, 1, 1. Is that okay? You look at this and go like, but Tech, I can see that those two columns are not the same, so they're not equivalent.
Is it because we don't need the last one?
Exactly, the last one cannot happen. X being 1 and y being 1, in this case translating to C of xi, yi being 1 and C of qi, ki being 1, cannot happen because of these two implications. If one is 1, the other one is guaranteed to be a 0. Okay, can they both be zeros? Yeah, they can both be zeros. Those implications doesn't say anything about can they both be zeros. It simply says if one is a 1, the other one has to be a 0. That's all it's saying, right? So that means this entire row is irrelevant. It cannot happen in this specific case. So if that row doesn't happen, and look at the remaining columns, go like, hey, they're both the same now. So that is why we can now use a or instead of an addition when we are trying to compute k of I plus 1. So this plus here, which was here, is now being substituted by a or. That's the mathematical symbol representing disjunction or. So if you're taking your notes, you can say bar, okay, because it means exactly the same thing. Or you spell out or, whatever you want to put in your notes, it's fine. What is the bottom line here? Why is this important? This is important because now we got rid of an addition. We turned the addition into a logical or, and we already know a logical or can be implemented by NAND, and the NAND can be implemented by transistors. Very good. So I'm trying to reduce everything so that it can be done using transistors. Because the proper name of this class is not assembly language programming for microcomputers. The proper name of this class is computer organization. What is inside the processor? We know what is inside the processor. Lots and lots of transistors. So now the question is, how can those transistors be doing things that we want it to do? In this case, addition. So are we doing okay so far with this? All right. So now we go back to the notes, and then we ask, remember last time I asked you this question of, well, these equations, I mean, these functions, C and R, they work for base 10, okay? We double check the logic and everything seems to be fine. They work in base 10. But what about base 2? How do we change this to work on base 2? That was the question. And the answer was, we change the 10 to a 2. So if you change this 10 to a 2 and change this 10 to a 2, then these functions will work in base 2. Now, except in base 2, x as a single digit has a range of 0 to 1, exactly, because it is now in base 2, a single digit can only represent 0 or 1 in that case. Okay, so now what I'm going to do is I'm going to copy this code here into Joplin just so that I can modify and talk about it. So Joplin is kind of cool because you can use a block of code and it will do the syntax highlighting for you like that. How cool is that, right? You're taking your notes, you're typing in some C code, and it's already syntax highlighted with all the fancy stuff. So now I change this to a 2, okay, and we change that to a 2. And this is where I really want to, pitch, let's change from base 10 to base 2, because how long do you think did it take you to learn the addition table for base 10? In other words, you have to memorize that 6 plus 7 is 13. It is not easy to visualize because it's exceeding 10. So that's still a pretty big table, even though addition is commutative, which means if you know what is 6 plus 7, you also know what is 7 plus 6. But that only reduces 1/2 of the items. It's still a pretty big table for a young person to memorize. Is that making any sense? So let's look at base 2, okay? So I'm going to construct a table in Joplin. It has the ability to do it. It's just, it doesn't, oh, wait, it's actually pretty easy. So it's x, y, and let me scroll up so the people in the back can see it. So it's x, y, and then we have r of xy, and then we have c of xy. And we'll see what this table is going to look like. Okay, so we have that, and that turns it into a table automatically. That is kind of cool. So x can be a 0, y can be a 0 at the same time. And we'll try to answer these questions in just a little bit, so I'm going to leave those items empty for now. And then we'll paste, and then change this to 1, change that to 1, and then both of these are now 1s. All right, so I'm just going to scroll down just enough so that you can see the C function as well as the R function. So now we are going to ask, what is R of 0, 0? I mean, that one doesn't even depend on what base we're dealing with, right? What is R of 0, 0? So we're looking at what? 0 plus 0 mod 2. 0 mod 2 is 0. Very good. Okay, so that's not too difficult. What about, oh, okay, 0. What about the R of 0, 1? It's 1, okay. And then the R of 1, 0? 1, because addition is commutative, right? So this is the only case where it's a little bit odd, because what is the R of 1, 1? 0. Oh, man, you guys are getting it. You don't need me to be teaching here. Let's go back to online where I just flip a switch and you guys just do your own stuff until the end of the semester. It's 0 because 1 plus 1 is a 2. 2 mod 2 is 0. Okay, but one thing is kind of cool is you can see R of xy is always just zeros or ones. Okay, that gives us some hope. Okay. All right, so let's work on the C column, which is even easier. So if you look at 0 plus 0, is it greater than or equal to 2? We're talking about this spot here? Nope.
No.
What about 0 plus 1? Is it greater than or equal to 2?
No.
What about 1 plus 0?
No.
What about 1 plus 1?
Yes.
Okay. So you look at the columns corresponding to R of xy and the column of C of xy, where x and y are individual digits in base 2, a bit. Oh, by the way, do you know why we have a term of bit referring to a digit in base 2? Go ahead.
Stands for binary digit.
Yep, it stands for binary digit. The B comes from binary, and then the IT comes from digit. Yep. And then we have byte, which is B-Y-T-E. You know, one byte has 8 bits. All right, so getting back to this table. So do you see, let's start with carry, because carry is the easy one. Do you see a Boolean operator that would give us exactly the same column for C of xy? Ampersand, logical and, would give us exactly the same thing. Wow, that is kind of cool, because now I can say, this is really the same thing as x and y. Or if you prefer, you can use the wedge symbol, but it's logical and. The only one, the one that is a little bit harder to figure out is R of xy. Because R of xy is not and, it's not or, it's not NAND, it's not NOR. It is something that we call exclusive OR. So that's one way to represent it, is X exclusive OR with Y. And then some of you are saying, yeah, but we never learned what is exclusive OR in CISP310. There is an exclusive OR operator, but it's a bitwise operator, not a logical operator. So technically speaking, you guys never used exclusive OR as an operator. So we look at that and go like, okay. Can we translate exclusive OR into just regular NOT and OR, that sort of stuff? The answer turns out to be yes, okay? So in this case, you can look at this as not X and Y, or X and not Y. And somehow that broke the table because of the bar. So if I use backslash, does it help? Yep. Backslash is escape, it works in almost every context. So if you focus on the right-hand side, okay, you can do it, okay? I'm not going to do it, but you can basically evaluate not X and Y or X and not Y for each row and double check that we do get all the zeros and ones as we have shown here. So, okay, I'm going to work out one row, okay, just so that we work it out. Let's look at the second row where X is 0, Y is 1, okay? So now we have not 0 and 1, and that's a 1. But since the overall thing is an OR, that means we end up with a 1. So that matches the one that we put here. Okay, but you can do it to all the other 3 rows just to double check and verify that the truth table is indeed correct. So what, right? I mean, there's always the so what. I mean, we go through all of this stuff here, translate, recognizing that all of this stuff here can now be done using logical operations. So what? Well, the so what means we can now go back to the C code here and say for base 2 only, okay, we can now say, hey, we don't really need this anymore. Because now we can say, we still want to return just 1 or 0, so it's a good idea to kind of keep that ternary operator. But now we can say, hey, it's just logical and. It would do exactly the same thing as a addition followed by a comparison. What about R? It is exclusive OR, but since we don't want to do exclusive OR, now we can replace this one and say it is not X and Y, or X and not Y. And just to be safe, I'm still going to use the ternary expression to basically limit what it can return to be just 1 or 0, just to be safe. Are we good so far? All right. So once again, we look at this change here and ask, so what is the big deal? Well, the big deal is we got rid of the addition and the comparison. And by doing that and replacing those operations with logical and, logical not, and logical or, in last week, we saw how we can convert a negation into NAND. We saw how we could convert logical AND into NAND. We also saw how we could convert a OR into NAND. So that means everything can now be done using NAND gates. Lots of those, tedious, yes, but nonetheless we can. And NAND gates can be done using transistors. So now we're looking at the R and the C function, and we now say, oh, both of those can now be done using logic gates, which also translates to transistors. So are we making that connection, all the way down to, the N and the P transistors that we saw on day one of this class? All right. So now that we have these things, okay, let me just kind of give you the definitions again, because this is really important. So the definitions that we have starts with Q. Q of I, if you look at it from the binary perspective, so let me just kind of emphasize that this is in base 2. This is how you make a section header in Markdown, is to use a pound sign. So I'm also teaching you Markdown, alongside with all the other stuff, But if you don't want to learn Markdown, there's no problem. I'm not going to give you questions in the final exam and say, okay, convert this, formatted string into Markdown. Yeah, that's not going to happen. All right, so Q of I is defined to be R of Xi, Yi. But now that we know R in binary is just exclusive OR, we can use the long, version, so I can go ahead and use the long version here. So it's the logical negation of Xi and Yi, this whole thing, or Xi and the logical negation of Yi. I mean, it's nothing new. It's just a new way of looking at those. And in this class, a lot of times I prefer the shorthand. So the shorthand in this case is just Qi is not Xi, Yi, or Xi and not Yi. So just kind of focus on the right-hand side, because the right-hand side has the double back tick. So in this context, you have to remember that Xi, Yi are Boolean. So what looks like a multiplication is not a multiplication. It is a logical AND. What looks like an addition is not really an addition. It is an OR. So the context changes what the operators are representing. All right, so that's one. The other one is even easier. Okay, C of I is really just the AND between Xi, Yi. So C of I is K of I. So K of I plus 1, I plus 1, there we go, is Xi, Yi. So let me do X of I and Y of I, or Q of I and K of I. And I'm going to put in some extra parentheses just to emphasize the AND happens first, like so. And we have one more, and then we are done with expressing how the bits relate to each other. So the last one is the S of I. So S of I is the same as Q of I, so I'm going to do the lazy thing and just copy and paste and then just change the individual item. So S of I is the exclusive OR between the Q and the K. So that's all I need to do here. Oops. Once again, Q and K. There we go. All right. That's it. This is just re-expressing everything that we knew about base 10, multi-digit base 10 addition, but this time it is for base 2. So now I claim that, hey, we now know how to perform addition in base 2. using just transistors. Because we have addressed, because we start with xi and yi, those are all given to us, right? So that means, we don't have to worry about where is xi, yi coming from, okay? Those things are all given to us, not a problem. So that means Q of I is easy to compute because it only makes use of things that are given to us. So it's not a problem. But once we know the Qi, we can now plug in the Qi, and K0 is also given to us. So we know that at least for K1, which makes use only of the bit zeros, we know how to deal with this. But once we know K1, we can use it to compute K2. Once we know K2, we can use it to compute K3, and so on. Once we have all the K and the Q, and then we can now compute what is the sum bit, which is the actual thing that we want, is actually, okay, what is the sum? Are we doing okay so far with the structure of multi-digit addition? Okay. Do you guys still remember the whole journey? How we started? We started off with base 10 addition. Then we analyze how we perform base 10 addition, and then we realize, oh, we need to refer to the single digit sum, which is just the sum mod 10 between the digits. And we also need a way to determine whether there's a carry bit or not for the next digit. We started with that, which is how we perform the usual base 10 addition. So we extracted the structure of multi-digit addition using something that we are familiar with, which is base 10 addition. Then what I did was to formalize by introducing the nomenclature. This is row X, this is row Y, row Q, row K, and row S. And then the digits are separated into column 0, column 1, and column 2. So now everything has a place. I can refer to all the individual digits, still in base 10, right? And then I looked at how the C and the Q, C and the R, the single digit, and also the carry are computed, and I came up with these two functions. So that completed the discussion using base 10. And then I suddenly throw a wrench into this entire discussion and go like, what about base 2? And then all of you recognize and go like, oh, so the only thing we need to change is change this 10 to a 2, change that 10 to a 2, and we are good to go. And that's what we did. But after we did that, we recognized that we have a special case where everything can now be replaced by Boolean or logical operators. And that was the last step, because once we know that the R function and the C function can be implemented using Boolean/logical operators, we now suddenly recognize we got everything now. Everything can now be done using transistors. So this is the part where I would go, woohoo, yes! Because it is a big deal, okay? Because when I was a student taking what is equivalent to this class, this was never taught, okay? And they never introduced, logic gates and, that kind of stuff, in my entire, educational background. So this is a very interesting moment, for myself also, because this is where I made the connection to go like, so that is how transistors can be used to implement computers. Yes, we only know how to do addition at this point, but it's still a big deal. Yep.
Is it like a big deal too because all you really have for a computer is just addition, subtraction, multiplication, division, and if
Yep.
you have addition, you can figure out.
So at this point we only have addition. We don't have subtraction yet. So we are going to get to subtraction in maybe 2 class meetings, and when we get there, you guys will be super disappointed. Because you might be thinking, oh, so we got to go through all this exercise and all this math and all that stuff. No, in the end, we just need to negate one bit somewhere within the circuit, and then we turn an adder into a subtractor. It is very, very simple. It's a very simple change to make an adder into a subtractor. It is super disappointing. When you guys are all thinking, oh, it's going to be something like this, you're like, no, it's really just flip that bit, and now we have a subtractor.
Sometimes disappointments are a good thing.
When the difficulty level of something is less than what you thought it would have been. Yes. Yeah, those moments do happen occasionally. Use sparingly. All right, so my watch is buzzing, which means it's time to take roll. I know how it sounds like, are we in high school? Well, we're not in high school, but still, I have to take roll because the funding of the college depends on that. If the accreditation organization asks, sometimes we may need to provide proof that we actually can show that people are showing up in our classes. Because if we cannot, the college can potentially be scamming the state and claim that, yeah, we have a full class. Look at all the 33 students that we have in this class here. And then we ask the state to fund us for 33 students in a class like this. That would be fraudulent, right? So I need to make sure that we take roll so that cannot be fraudulent. All right, so the two words for roll taking is MBTI, all in lowercase, or all in uppercase, but the activity is not released yet. So let me go ahead and release it first. So MBTI refers to the Myers-Briggs type indicator, which is a way to assess personality types.
So, Professor?
Yep.
I seen that in those modules that you added, and I looked at the chart that it says that the personality types, programmer jobs, people that it was like a link to your Yahoo Answers, and mine's is below the line, and then I got a sinking feeling in my stomach.
Well, those are really just a indicator, but it's not definitive. So I wouldn't let it bother you too much. So now you guys can all participate in the roll-taking activity of today, which is August 31st. And the words to use is MBTI all in lowercase or MBTI all in uppercase. So back to your question, your sinking feeling thing. I think what you should take out of the personality test is to figure out how to study so that your strength is going to help you in the endeavor. So depending on what your type is, I'm just using an example. Let's say ISTJ. Okay, so in that case, those people tend to be more detail oriented, which is a good thing. They tend to be more studious. They're less likely to be distracted. So for those people, to succeed in a class, in computer science, they can benefit from pairing up with somebody who is one of the NT type of people. So they can basically look at, okay, so by communicating with somebody else, who is of a different type, we pick up stuff from the other person.
That's interesting.
Yeah, so I think I wouldn't use the MBTI thing to basically, it is not a predictor. It is more like, this is what we think you are, and sometimes the test may not be accurate either, but it gives you an idea of what strengths you have and what may not be your strength. So this way you can figure out a plan to utilize what is actually your strength to help you succeed in the class. So I would look at it that way, as a way to navigate. I'll give you an analogy. So let's just say that this is point A, this is point B, okay? There's a desert in between, but there's also a highway that's kind of zigzagging through the desert. So if your personality type says you're a dune buggy, you just go straight through the desert, right? Because that's what you do best.
Right.
But if your personality type says you're a Corvette, which is about this close down to the ground, you may not want to go over the sand hills.
Right.
Because with your summer tires, you won't have traction. You'll just be throwing sand all day long. So instead, you're going to take the zippy line. It's like I can do a highway and I can really turn. I can handle. So you'll be going this when the dune buggy is not really fast, but it can go like that. So I'm going to look at it that way. Is you can choose what is the best route for you to go from point A to point B.
That makes sense.
And some personality types are hot air balloons, like
Yeah.
myself, right? So I just kind of float up at the right time of the day when the wind is blowing in that direction and hope that the wind does not change direction along the way. That's my type. It was just a hot air balloon.
Yeah, I notice I'm more like a rabbit hole
I'm
type of
filled
guy.
with hot air, yes.
Yeah, I
So
just
I would look at it that way. It's basically you just have to figure out what you are. You're still going from point A to point B. You just need to figure out what is the best way for you to finish that journey.
that makes sense.
Yep. All right. So now that we are done with MBTI, which is going to be in your final exam. No, not really. I'm just
I was like,
kidding.
really?
Yeah, that's what hot air balloons do. Is they just kind of give you guys things that go like, are we really going to talk about that? No, not really. Okay, so by this time we are done with all of this stuff here and multi-digit addition, which start with base 10 examples, blah 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 blah. And now we are done with this also. Okay, how does a computer do this using transistors? So now we're going to get to this part here. Implement a 3 by 3 bit binary adder using AND or NOT gates in Logisim. Okay, because now we can actually get to visualize. Okay, because I presented the equations. Okay, the equations are all here. So focus on just this part here. This is what we write down as equations. But what does the circuit look like in order to get this done? So that's what we're going to do next. All right. So the rest of today's lecture is just me working on Logisim and explaining along the way, how those equations translate into circuits in Logisim. So let me start up Logisim first. And in case anyone is wondering, my MBTI is an INTP.
INTP.
INTP. Yep. So java-jar in my downloads folder, Logisim. There we go. And of course, it has to start on the wrong screen. There we go. All right, so we're going to start with making an exclusive OR gate, because it doesn't, because we want to simplify things a little bit. Yes, so for those of you who say, but Logisim already has exclusive OR, which is right here, I'm just going to say, well, let's assume that it does not, okay? So if Logisim does not have exclusive OR, I'm going to make my own. And to make my own, I need AND gates. And the default AND gate is way too much, too big, too many inputs. So I just have to change all of that stuff here. Duplicate it. Control D is duplicate. And kind of move them around a little bit so that the resulting circuit looks a little bit better than my usual. And then we have to say one input goes in without negating, but the other one has to be negated. So one thing that's interesting about Logisim is you can negate the individual input pins. So you can pre-negate before it goes into the AND gate in this case. So that's really neat because I can just use this feature to pre-negate the top one on the first AND gate and then pre-negate the second one with the second one. So now it is just a matter of feeding the first pin to both of the top pins and then feeding the bottom pin to both of the bottom connectors, like so. And then whatever is coming out of this is going to be ORed. So now I need to extract, create an OR gate. So once again, it's way too big, too many input pins, typical things. There we go. And then we just have to OR the results of the two ANDs.
How do you change the size?
Hmm?
How do you make it small?
Make the gate size narrow instead of medium. It's just cosmetics. It doesn't really change the function of the thing. It just uses less room on your screen. And then whatever is coming out of the OR gate is my output. Okay, so now I just need an output pin, slap it right here, and voila. I got my exclusive OR thing made out of negation and OR. You don't have to do this because there's actual exclusive OR already built in to Logisim, but I do want to show you this diagram just so that you can look at this diagram and then you can go back to the equation, which is here. And so you can actually see how this expression here is exactly the same thing as what we have in Logisim. By the way, this is X, this is Y, this is X exclusive OR with Y. This is the first half of the OR, this is the second half of the OR. All right? Well, this is all getting recorded, I hope. Yep, it is. So this way you can always come back here if you want to, to take a look at this. So once I'm done with this, I'm going to go to the circuit. It doesn't make sense to call that main anymore, right? So we'll call this exclusive OR because that's what it does. And we're going to change the appearance and also mention that this is our exclusive OR, XOR. There we go. Yeah, just as documentation, it's nice to know what it is. And there we go. All right. So it's going to be helpful because now we don't need to slap a gigantic complexity of circuit a lot around the entire design. So what do we need to do next? So we're going to go back to Joplin, and this time we're going to say, all right, so you can, okay, I hope you guys can see this. Do you see how QI and SI are structurally the same, even though they're utilizing different inputs, but they're structurally the same? Okay? And at the same time, the bits that I use to compute QI is also used to compute 1/2 of K of I plus 1. And the bits that I use to compute S of I is also used to compute the other half of Ki plus 1. Do you guys recognize that? So because of the structural similarities, now I just go ahead and combine and say, okay, so maybe I can make a thing in Logisim that can compute Q of I and 1/2 of K of I plus 1, because that same structure will also be used to compute S of I and the other half of K of I plus 1. Because this way I can simplify the design and just kind of slap the same thing over the place and just make sure that I connect those things correctly to get the end result. So I'm going to look at Q of I relative to Xi and Yi and make a circuit out of that first. Okay, that would be pretty easy. So I'm going to create a new circuit, and it is called a half adder. Okay, I'm just using HA to represent half adder. It's going to have 2 input pins, okay, like so. And the first thing we do is to try to compute, assuming these 2 input pins, one is X and one is Y, the first thing I want to do is to compute Q of I. But Q of I is really just the exclusive OR, so that means I can now utilize the circuit that I created earlier and say, okay, we'll just go ahead and slap an exclusive OR here. And then the output of the exclusive OR is already 1/2 of the answer, which is Q of I in this case. But at the same time, we also want to compute 1/2 of K of I plus 1. So if I switch back to the notes here, 1/2 of K of I plus 1 is just a regular AND. So now I just go ahead and pick up an AND gate and do the same thing, make it narrow, change the number of input pins to 2, and slap it about here. And that would be the carry 1/2 of K of I plus 1, and I'm going to stick it here. So once I got this, I'm just going to do the same thing here, here, and then this one has to go to here, and also here. And then the output of the exclusive OR is the Q, and then the output of the AND is 1/2 of the K of I plus 1. Are we doing okay so far with this? Okay. So let me comment, okay? Let me just kind of label the pins, because this way it's easier for you guys to visualize what we have done so far. So I'm going to label this pin. I'm not going to use XY because that's confusing because the overall circuit has XY as well. So I'm going to use, I don't know, A and B. And then the output is like trivial because this one is just A exclusive OR with B, otherwise known as R of AB. And then this one here is C of AB, which is also known as A and B. All right, so are we okay with the labeling? All right, so now I'm going to switch to the circuit appearance and kind of do the same thing because I really hate to have a circuit where things are not labeled and I have no idea what it does. So I'm going to have A, B, and then we have R of AB, and then C of AB. And there's no easy way to make things line up really nicely to begin with. So I'm going to have to move it around after the fact, like so. It's not too bad. It's just, tedious. There we go. And this is our half adder. So now we have the half adder done. It's time to make another circuit. So add another circuit. This time it's called a full adder. So a full adder, so if we look at the picture here, each half adder, let me see if I have different colors for slide board markers, because I need two different colors. Okay, have a red one, make sure it is a dry board marker, because one time someone used a permanent marker as if it was a dry board marker. That did not go too well with the dean. All right, so the one half adder is going to say, we'll take these two as an input and produce that as an output. XY creating the Q, except this is in base 10, that is in base 2. Okay? The other one is going to take these two and create the sum. Is that okay? Because the structure to compute Q coming from XY is the same as same as coming up with the S from the Q and the K. But each one is also going to contribute 1/2 of the carry bit. Because we are using C of XI, YI as 1/2 of the KI plus 1, or K1 in this case, we are also using Q0, K0 in order to compute K of 1. But the way we use the bits is identical in terms of the structure. Is that okay? Are we doing okay so far? Kind of recognizing the similarities of this. One half doing this, the other half is also doing about the same thing. Structurally, they are the same. So the question is, if we need a full adder, which means we take everything into consideration, everything on one single column into consideration, just to compute the carry bit of the next column, the only thing that is missing is the OR. How do we combine the two individual carries of the half adders? So we need an extra OR to do that. So for the full adder, the first thing we need is to say, okay, we need two of these. Okay, so we need two of these. And the question is, what are the inputs into each full adder? So what we can see is, okay, we got XY. Okay, so now we can actually refer to the pins XY because they are actually referring to the XY row in this diagram. So we got X, and then we got Y. Okay, we can just duplicate this one and then rename it to Y, like so. What else? The carry bit is the other input. That's our third input, is the carry bit from the previous column. So we need another input pin for the carry bit. And what are we supposed to get out of this? Well, one thing we should get out of this is the sum bit. Okay, so we look at the output, and it is an S, which is the sum bit. And we also have a carry out, which is this thing over here. So we have a carry out. So we can call this one carry in, K in. And then we have another one, which is K out. So let me move this one here, and we'll call this one K out. So right now, I have just defined the interface of the full adder to whatever is outside of the full adder. In other words, if you think about a circuit as a part of a C program, I'm defining a function. The pins, the input pins, as well as the output pins, those are kind of like parameters when you're defining a function. So now I need to figure out, okay, what is inside the function? How do I start with the input parameters in order to compute the quote-unquote output parameters? All right, so we know that x and y should go into one of these thingies. Okay, so let's go ahead and do that, right? X and y would go into this one. What is going to be the R coming out of this? Is there a name for the output coming out of this particular port of a half adder? In other words, if X is A, Y is B, what is R of XY? Does it have a name? Okay, let me give you a hint. It may not look clear here, but all this is Xi exclusive OR with Yi. So what is the other name of that computation? Q. Very good. So how do we use Q? Q is used here. So Q is also exclusive ORed with Ki to come up with Si. Is that okay? So now we know how to wire this thing up, because now we say, oh, that in return is going into one of the inputs of the second half adder, and then K in is the other input into the other half adder, and then the R of that thing turns out to be this thing that we need here. Is that okay? I just want you guys to focus on the diagram at this point to understand how we compute S of I from X of I, Y of I, and then K of I minus 1. Because K in is I of I minus 1. It is coming from nope, I take it back. K in is actually Ki as well. Okay, take it back. K in is actually Ki. But I'll be seeing how it is done. Okay. So what is left now is to ask, what about K out here? Now, assuming the circuit is done, everything up to this point is done correctly, we now have one output pin, but two output pin as in K outs, but we have two ports of the half adders that are not used. So we kind of can guess that something has to combine C of AB from the first half adder with C of AB from the second half adder in order to come up with K out, right? And what would that be?
OR gate.
An OR gate, very good. How do we know it is an OR gate? So we go back to the equation here, and we see this is C of XIYI. This is C of QIKI. What connects those two to become K of I plus 1, which is K out, is a single OR. Okay, so now we go back to the circuit, and we say, oh, okay, so we just need a little OR gate here. Once again, it's going to be too big. Make it smaller. Change the number of inputs to 2. And what did I do? Oh, I changed the data bits. Okay, that was stupid of me. There we go. Change that to 2. And okay, I'm going to move things around a little bit just so that it looks nicer. I mean, the other way would work too. It's just going to be wires flying all over the place. There we go. We take one of the CAB. This one is technically C of QIKI. This one is C of, oh, that is not going to work out well, does it? It'll still work, just not nice looking. There we go. Because let me highlight the wires. This wire is C of XIYI. This y here is C of Qi. So when you combine those two using an OR, it becomes K of I plus 1. Are we doing okay so far with this diagram? Or at least the rationale going into this diagram here. All right? Okay. So now it's time to turn the full adder into a diagram. So we go to Edit Appearance and just have to do some labeling. So we got X, we got Y, we got K in, and then we got S and K out. So now we just have to move these things around so it looks kind of nice. I think we can put X here. We can put Y here. K in is a little bit too long. I'm going to have to put it outside. K out is also too long. Kind of put it outside. And then the sum bit is going to go here. There we go. Okay, I think it's acceptable. Not the best looking kind of design, but it's going to work. All right. So now we're going to create yet another circuit. This is actually our main circuit now. So the assignment was to create a 3-bit by 3-bit adder. So that means we have 3-bit input as our X, and it's going to be 3-bit wide. And then we also have another input that is labeled Y. It is also 3-bit wide. And then we have out as our output, it's going to be sum, and it also has 3-bit. And then it will have one extra pin left for the overall carry. So we'll just call this one the overall carry out. Oh, by the way, I forgot one thing because we have a carry in. So this is going to be our first carry in, and I'm just going to call this one K0 because that's what it is. So carry out is technically K3, so let me change the name. So this way we know exactly what it is. Okay, we have K0 being an input pin, K3 being an output pin of the overall circuit. All right, so what do we do next? In other words, of all the sub-circuits that we have created up to this point, one is called exclusive OR, one is a half adder, one is a full adder. Which one do you think I'm going to slap onto this main circuit here? Sorry? If I put a half adder here, that means I have no use of the full adder, right? Because the full adder is made out of half adders. A half adder uses exclusive OR. So if this is main, that means I'm very likely to be using what?
Full adder.
The full adder, because the full adder was the last product. It makes use of everything else that I created earlier. So we're going to use a full adder, and we're going to need 3 of those. So we'll say duplicate and duplicate. There we go. And you go like, oh, that's easy. They're labeled X and Y, so we just hook up X to X, Y to Y, and K in to K0, and everything should be good. You go like, nope. Well, that's because X as an input pin is 3-bit wide, but the full adder is expecting X to be a single bit. Okay, so it's not going to work out just by a direct connection. So what do I need to do? The input pin has 3 bits, and then the circuit that I want to actually use to do all the calculations has a 1-bit pin. So what do I do?
You need a splitter.
We need splitters, not just one. We got a few. We need a few. So we'll go ahead and pick out some splitters, and you guys tell me what we should do with the splitters. How should we configure the splitters?
So the bit width should be 3.
Yep, exactly.
And the fan out should be 1. No, I don't know. 3.
It should be 3, exactly, because we need all 3 bits. We just feed the 3 bits to different places, right? So each full adder will take on 1 bit from X, 1 bit from Y, and the carry bit is the one that is kind of interesting. We'll deal with that later, okay? All right. So I'm going to duplicate this because I need 3 of those things. So I'm going to stick one up here and then duplicate one more time and stick one down here because we need one over here in the output as well. Because the output sum bit is only single bit, but the output sum bit, as a pin, has 3 bits. So we have to combine each sum bit from each full adder into the 3-bit output. Okay? So we need 3 splitters for this purpose. Okay. So now we got this. Okay, no complaints, which is great. And now we need to hook up bit 0 to the first one. I mean, you guys can flip the order if you want to, but I'm just going to go with that specific order. Like so. Oh, I got it wrong. Sorry, don't copy that. All right, so this is good. We need Y0 to go to the same half adder. In other words, I'm trying to, this particular adder here, this is a full adder, it is in charge of column 0. This one is in charge of column 1, this one is in charge of column 2. So if you look at this diagram, in order to deal with column 0, we need XY, and then we also need K0. So that's why K0 is the one that needs to go here. And I need to be very careful with how I route the wire because I don't think I left myself a lot of room to move things around. All right, so if those are the inputs and this adder here is supposed to deal with column 0, where should I hook this up? This is actually going to be which bit of the final result of sum are we dealing with here? You only got 3 choices. It's either bit 0, bit 1, or bit 2. This is, okay, let's look at the input here. This is X0, this is Y0. So which bit of the S row are we talking about? Bit 0, very good. All right, so let's go ahead and flip this thing around and do some connections. So we got, okay, that should work out okay. So that one goes here. Great. So now we have this thing coming out and go like, okay, where is this supposed to go? What is this? Well, what you're seeing on the projector, as a dangling wire, is our K1. That is K1. So you can label it if you want to. Labeling is just using a text tool, but it is K1. So now the question is, how do we wire up this thing here? What do you think? This is in charge of column 1, right? So what bits from X and Y do I need for port X and port Y of the full adder that I have highlighted? Yep.
Do you need bit 1 from X to go into the input of X there?
Yep.
And input, Y's 1 goes to the Y input there on the same full adder.
Mm-hmm. And what about this guy here?
Yeah, from the previous one, go to the.
Yep. Exactly. We are going to change things up a little bit here. And obviously, I did not plan out the diagram very well. So now we have some convoluted, wiring. There we go. I mean, logically, it still makes the connection. It's just, kind of ugly to look at. What about this one here? How should I wire this thing up? Yep, it goes to bit 1. Oops, not that. That one. There we go. Cool. All right. What about this guy here? Where should it go? You guys already answered the previous question, so this one should not be too hard. This is carry out from bit 1. Yep, it goes to the carry in of bit 2, which is K2. All right, so we go all the way around because I need that routing resource to do the other bits. So we just stash it here. What about this one here? Where should it go? It has a label of X, but this is the full adder in charge of column 2. So where do you think this should be wired up to? Bit 2 of X. Very good. All right. So I think we barely have enough, room for this routing. What about this guy? Bit 2 of Y. All right. Yes, that kind of works out, just barely. All right. What about this guy here?
That goes to the last, this, the last bit on the output. So X is 2, or S is 2, I guess.
Yep, bit 2 of the merger or splitter. There we go. What about this guy here?
And that just goes to the output K3.
Yep, there we go. Woohoo! Yes, so now we have a 3-bit by 3-bit. This is called a carry ripple adder. Why do you think it's called carry ripple?
Was Carrie Ripple the lady that they named it after?
No, because until K1 is done, K2 is just, okay? It's not an error per se. It's just that it gives you something that is not the answer, okay? So if you look at how things are organized, X, Y, and K0, they're all presented to you right off the bat, okay? So you don't have to wait. But it takes time for bit 0 or column 0 to compute until the time that its K out makes sense, okay? But until K1 is making sense, column 1 can start computation. But until K1 is correct, then K2 is not going to be correct. But until K2 is correct, K3 is just some mumbo jumbo. It may not be correct. So that means this has a rippling effect because we start off with bit 0, but until the full adder responsible for column 0 is done, the column 1 cannot start. Until column 1 is done, column 2 cannot start. So that means if each full adder is taking X amount of time to do all the computation, the amount of time taken by a n-bit adder is going to be proportional to n. The more bits you want to add, the longer it's going to take for the final answer to be correct, which is a problem because now if you have a 64-bit adder, it's going to take 64 times the time that is otherwise required to compute the sum of a single bit. Okay, so that is a problem. All right, so I know we are running out of time, but I do want to show you that this works, right? Because otherwise, you look at this whole thing here and say, well, TAC kind of claims that it works, but how do we know it works? So, okay, give me some ideas. What do you want to add?
7 and 10.
We cannot specify 10.
Oh, 7 and...
So with 3 bits, the range that we can specify is 0, 0, 0, which is 0, up to 1, 1, 1, which is 7. So give me 2 numbers where the sum is, okay, let's just deal with the sum being within 7 also. So give me some ideas.
0, 1, 0, and 0, 0, 1.
Say that again.
0, 1, 0 for X, and 0, 0, 1 for Y.
Okay, 0, 1, 0 for X, which is 2, and then
0, 0, 1.
0, 0, 1 for Y, which is just regular 1. So, okay, so before I click it, what are we supposed to see if we're adding 0, 1, 0 and 0, 0, 1? We should be expecting 0, 1, 1, which is 3. Okay, so we try to make sure that happens. Woohoo, that works. So I'm going to give you some more tests, okay, just one more. Let's try to change it to 1, 0, 1, which is a 5 plus a 3. So 5 plus 3 is 8, right? But 8 cannot be contained in 3 bits because 8 is 1, 0, 0, 0 in base 2. So it requires 4 bits. So what you're seeing here as the answer is really the same thing because the least significant 3 bits are 0, 0, 0, and they are represented by the sum, output pin. The extra carry bit, that's the 1. So we are actually getting a result of 8. It is just breaking up the most significant digit from the other 3 digits, that is also a part of the result. So let me just say that, yes, it seems to work, but it has this problem of, it cannot be computed really quickly. So next Monday, when we come back from the long weekend, Monday is a holiday. So next Wednesday, okay, so next Wednesday when we come back, we are going to, okay, let me go find the right page. So we are going to go to a very um, unassuming, topic, which is, but wait, there's more. But if you have ever watched infomercials, you know there's a lot that they have to say whenever they say, but wait, there's more. Okay, so this is the part where we optimize the adder design so that it takes constant time. The amount of time it takes for a 1-bit adder to perform its operation is quote unquote the same as a 64-bit adder, as a 128-bit adder, and so on. So there's a trick that we can do so they can do something like that. Okay, that's what section 6 is all about. Okay, it is a very complex section in a way because there's some derivation in Boolean algebra, but in the end, it results in something that is really useful. Okay, so read ahead of me. Try to read as much as you can in section 6. So now we're going to transition into the lab time. Give me some time to prepare the lab. This is not going to be a really long one. It is Logisim based. So if you don't have a thumb drive with you or your own computer with Logisim on it, you can go ahead and download Logisim again and put it onto the school's computer. So I'm going to go get that prepared. If you want to go take a break, 10 minutes, that's fine. It won't take me much time to set this up. All right, so the access code is multi. All right, well, officially it is available. If you don't want to take a break, you can get started now, or you can go ahead and take a break. Yep.
Quick question about adding more bits to the adder. Would you simply add more of the
Let me go
adders
back
to
to
the
that.
single circuit, or would you start nesting the circuits?
You mean with this one?
Yeah.
With this one, the easiest way to do it is to chain more and more full adders. If you do, nesting is not going to help in this case because each one is only a 1-bit by 1-bit adder. Now you can try to construct, like a 2-bit by 2-bit adder, and then use those to make up like 4-bit by 4-bit adders, but you're not going to save any time. Structurally speaking, it looks simpler, but in terms of time, it's still the same because within the 2-bit by 2-bit adder, you still have that ripple from the first to the second, and then from the first 2-bit by 2-bit adder to the second 2-bit by 2-bit adder, there's still a dependency between those two. So in terms of the diagram, it does look simpler, but in terms of the amount of time it takes, you're not gaining anything.
Because it's a linear.
Because it's still linear.
Okay.
Yep. But you can reduce the overall complexity of the looks of the circuit, but you're not changing anything in terms of the linear nature of the whole thing.
So you're just
Right. But the mechanism that we will be talking about next Monday, which is called the carry look ahead mechanism, that actually changes the time complexity. So it get rid of the linear dependency.
Let me see
Yeah,
here, man.
the trick is both simple and difficult. The simple part has to do with, we're just doing substitution. But the end result of the substitution just end up with a more complex gauge structure for each bit. So it's no longer something like this simple, where we can stamp out the same circuit over and over again. Now you have a special circuit for K1, a more complex one for K2, an even more complex one for K3. So we only want to do up to K3 because after that it's like it just gets really messy in Logisim. So that's what we're going to get into next Wednesday, not Monday, because Monday is a holiday. You guys are welcome to show up, but I won't be here. All right, so I'm gonna stop this streaming and then make that available to you guys so you can do whatever you want. Okay.